Hello. Next, we are going to present the presentation possible link between climate change and extraordinary wildfires in Australia, the Amazon, the Western United States, presented by Dr. Paul Baek. Okay, thank you very much. You can start with the presentation.
Thank you very much.
Compartir pantalla.
Thank you very much, Mr. Chairman.
No, no has compartido pantalla.
Compartir.
Ah, vale, dale ahora, comparte pantalla. Ahora, correcto.
University in the United States. The title of between climate change and extraordinary in Australia. The Amazon stakeholders are Milan, Brajkovic, Tom Carter, Charles Cook, and myself, Ahmad Purmabahid. Wildfire is defined as controlled and unplanned combustion of vegetation. And about 90% of wildfires in the United States are caused by people. Common causes of wildfires are campfires left unattended.
1 second, please. There is again a small problem with the
Ahora sí.
Start from the beginning. Yeah, sorry for the brief interruption. Causes of wildfire are campfires that are left unattended and high wind, down power lines, discarded cigarettes, intentional arson, and hard spent ammunition. And the remaining 10% of wildfires are caused by natural causes, which include lightning strikes, volcanic eruptions, decomposition of materials, and the average of 50,000 wildfires every year in the United States alone between the years 2010 and 2020. And 3.5 million hectares burned in 1 year alone, the year 2020, compared to 1.9 million in the year prior. Wildfires are obviously very dangerous. They can move as fast as 19 kilometers per hour, and humans often inaccurately estimate the distance the wildfire is away from them. And they have a sense of false security because people in size as approaches or moves away. There are some pictures from California wildfires 1 year ago. Leading factors are low soil moisture, low relative humidity, high temperatures, and fuel density, meaning how much vegetation is available to spread the fires. Some of this is linked to climate change, and since the 1800s Industrial Revolution, the global temperatures have slowly increased by approximately 1 degree Celsius, while the temperature in California has increased by 1.7 degrees, and this is this has been accelerated in recent decades, as shown by the data from NOAA. Map of the United States showing the vapor pressure deficit. The vapor pressure deficit is a measure of difference between the amount of moisture in the air and how much moisture the air can actually hold. So it is closely related to relative humidity. High vapor pressure deficit means low humidity, and the colors are shown here. So as you can see, in southwestern United States, there is a major problem with dryness or vapor pressure deficit. And the forest fire area in kilohectares is shown here as a function of fuel aridity signal, which is defined in this area as a deficiency of moisture, especially when resulting from permanent absence of rainfall. The red dots are for the years 2000 through 2015. The blue dots are from 1984 to 1999, and there's almost a linear relationship between the extent of fires, how much area of forest is burned versus fuel aridity. As you can see, most of the red dots are on the high side here, showing a clear rise in the amount of forest that have been burned recently. Which means that as we have warmer temperatures caused by global warming, the plants get more dry. Some of them die, and the dry ones are more prone to wildfires. So as they burn, they release a large amounts of CO2 into the atmosphere, which can contribute to more global warming, and this cycle just continues. And of course, the amount of fires depends on what kind of field we have. So as you can see here, grassland is more prone to fires compared to invaded woodland, shown on the far right side. The fire seasons are becoming longer and more frequent, as shown here. And these are the areas where the number of days per year have increased for the fire season. So you see a lot of it in Brazil, for example, Western United States, Eastern Africa, and the Middle East. There are different ways of managing vegetation. Making fuel breaks and prescribed burning here, so you basically cut off one section of the forest from another. Lots of wildfires in Australia in the year 2020, in which 16 million hectares burned and 3 billion animals were harmed or killed as a result. And I'm sure a lot of you have seen that on the news about a year ago. Some pictures of wildfires in the Amazon, primarily in Brazil. And some data on wildfires in Amazon from 2020. And there's a 61% increase in the area burnt compared to the year 2019. And the primary causes are negligence of humans and the very serious drought in Australia 1 year ago. Also, the extent of wildfires in Western United States has been compared to previous periods. And in 2020, about 50,000 wildfires started between January 1st and November the 6th, burning 3.5 million hectares compared to only 1.9 million hectares a year ago. And the year 2021 has even been worse than the 2020. Here we're looking at the number of acres burned, millions of acres versus time. So this is 1980 on the far left and 2019 here. And you see a general increase in the number of acres burned from 1980 to 2019. The fire radiative power is a very good measure of the intensity of wildfires. This is usually detected by satellite, detecting the radiation from wildfires from the sky. And we see data for California from the year 2003 to 2020. So clearly a very, very large increase in fire radiative power in the year 2020. Same thing for the state of Oregon, and for the state of Washington, this actually peaked in the year 2015. They could estimate the amount of CO2 released when we have wildfires. Generally, for every kilogram of wood completely burned, the 1.9 kilograms of CO2 are emitted. If you assume a clear cutting method, 215 tons of wood can be collected per hectare, and 4.2 million hectares burned in the western United States in the year 2020. So a very simple calculation results in 896 million tons of wood burned in that year during the western United States wildfires, which translates to 1.7 gigatons of CO2. As a matter of perspective, a typical passenger car emits 4.6 metric tons of carbon dioxide in 1 year. So that means that the wildfires in the western United States in 1 year were equivalent to an additional 370 million vehicles on the road for that year. In Europe, the extent of wildfires have been gradually going down. So we're looking at data from 1980 to 1989 here, and the last range here is 2010 to 2018. The green curve shows the number of hectares burned for the entire Europe, and the numbers are thousands of burned hectares. So for the continent, this is just for the Mediterranean countries, the wildfires have been going down, and we have data for separate countries here. This is Spain, showing a spike around 1995, going down after that. And we have data for Portugal, France, and Italy separately. Most of the fire intensity has been in the Scandinavian countries, Norway, Sweden, and Finland, is shown in the colors here. And there's more data on Europe. Due to recent climate change, fires have increased. There have been longer heat waves in many places, including Europe, stronger winds, and more frequent lightning. This is a picture of clouds that are formed when we have very large wildfires that combining with the moisture from the sea, and they often result in electric storms. There are many different ways to fight wildfires. One is to start prescribed fires, thin the dense areas, and clear out areas of vegetation. Sometimes grazing animals are used to prevent forest fires. And of course, there are aerial sprays of water or other chemicals that are quite effective in fighting fires. In summary, in recent years, there have been severe and unprecedented wildfires in many areas of the world, including the western United States, states of California, Oregon, Washington, etc., and they have become even more intense in the year 2021. So this year is even much worse than a year ago. It's not possible to link all of these wildfires directly and undeniably to climate change, but the data clearly points to a very strong possibility that such a link exists. In our opinion, climate change has contributed to the frequency and intensity of wildfires in the nations discussed, and they have affected humans and billions of animals. In many parts of the world, the vapor pressure deficit is increasing along with climate change, meaning a much more drier forest, prone to fires. Most of the wildfires were caused by human activity and negligence. And finally, the CO2 produced by wildfires in the western United States is equivalent to adding 370 million vehicles on the road for 1 year. This is a picture from May of this year. California wildfires have already burned 5 times more land than a year ago. And again, this is the title of my presentation. This is paper number 201. And the authors are Kettering University students, Marin Brachkovic, Tom Carter, Charles Cook, and myself, Amat Purmavahed, Professor of Mechanical Engineering, Kettering University, Flint, Michigan, United States. Thank you very much for your time.
Next paper will be what lies for energy and carbon emissions post-COVID pandemic.
Hello, my name is Soc the outline, we start with historical energy sources, continue on with historical CO2 emissions, global warming potential, contribution of agriculture to climate change, COVID-19 impact on CO2 emissions, and contribution of wildfires, and future outlook and the effects of electric vehicles. Here in the chart, we are looking at the global primary energy consumption by source, starting with the Industrial Revolution approximately 1800, and this is the year 2019, 1 year ago. As you can see, there has been a continuous rise in energy use, and different colors are used for different sources of energy. So this color here at the bottom is traditional biomass, which means primarily wood. This gray color is coal, oil is shown in blue, and natural gas in light purple, and others are smaller amounts here. So as you can see, most of the energy still comes from fossil fuels, which of course include coal, oil, and natural gas, and fossil fuels still supply 84% of the world's energy, in spite of all the increases in renewable sources in the last few decades. these are CO2 emissions by region. The numbers are in billions of tons, and this is the year 1751, and the year 2018 here on the right side. So again, we see a continuous rise, a significant one. This color at the bottom, the beige, is EU 28. The rest of the Europe is this color here, light pink. United States is shown in light blue, and so on. This is China, etc. So there's an alarming increase in the amount of CO2 being added to the atmosphere every year, resulting in a continuous rise in concentration of CO2 in the atmosphere. So these are parts per million by volume of CO2 in the atmosphere, and they're measured since the year 1958 in Mauna Loa, on one of the islands in Hawaii, pictured here on the right. And we can clearly see that we start in 1958 below 320, and we are now at about 420, and this is still going up by about 2 ppm every year. Global warming potential means that various greenhouse gases can be compared to CO2 in terms of their ability to cause global warming. So CO2 is obviously equivalent to itself, so its global warming potential is 1. Methane is 21 times worse than CO2. So 1 gram of methane counts at 21 grams of CO2. Nitrous oxide is much worse than methane. So 1 gram of nitrous oxide is as effective as 310 grams of CO2 in terms of its ability to cause global warming. So this formula here allows us to combine the effect of various greenhouse gases in a mixture and expresses as an equivalent amount of CO2. This slide here is looking very strange for some reason, but 37% of greenhouse gas emission are associated with the global food system, and they're primarily caused by cattle, like cows, emitting a lot of methane. Growing rice also releases a lot of methane, and of course fertilizers have a lot of nitrogen in them, which they are converted to nitrous oxide, which was, as you saw here, 310 times worse than CO2. Nitrous oxide is the same gas that is used sometimes by dentists as well as gas. Once again, methane primarily comes from animals like cows and from rice grains, and from fertilizers used in agriculture. See pictures of fertilizers and an article, emissions of greenhouse gas commonly known as laughing gas or soaring, and that's the same as nitrous oxide, N2O. Global average temperature increase to below 2 degrees C, and preferably to 1.5 degrees C. And these are countries that emit large amounts of greenhouse gases. For example, China emits about 24% of the global greenhouse gases, United States about 12%, EU 9%, and India around 6%. United States pulled out of the Paris Agreement in 2017, but rejoined again in February of this year. Renewable energies are growing very fast, and they grew by 30% from 2004 to 2014. Most of it comes from hydro, which is the blue area in this chart. Wind is shown in light red, solar is yellow, and other renewables are green. So all of these are growing rapidly, but again, that is about 16% of the world energy use. The other 84% still comes from fossil fuels. Here we're looking at global liquid fuels production and consumption from the year 2015 to this year, 2021. We see that both the production and consumption took a nosedive due to the pandemic here, but both are recovering and they're almost at pre-COVID levels. So clearly the effects of COVID on liquid fuels has been very temporary. Crude oil prices became negative for the first time ever, and the price was minus $37.63 US a barrel. This lasted for 1 day or 2 days, and that is shown here as this dip. This is very strange to have negative numbers, but it's because there was very little demand for oil, and if you had a lot of oil, you had to pay for the storage. So people will pay you to take away the oil, and the oil prices have again recovered to about $70 a barrel. We see a large dip in CO2 emissions in the year 2020, as indicated by this drop here. This is obviously a result of the pandemic. These are daily emissions for the year 2020 compared to the year before. And as you can see, for all of the year, all the way to June, the emissions were significantly less than before. And the same thing is shown here. Year 2019 is shown in blue, and you can see 2020 is significantly below that. So these significant drop in emissions, but this shows you data from 1900 to the present, here 2020 or 21. And the bars shown in blue are estimated emissions. So we see major dips caused by major events, such as the World War II, for example, which is here. This dip here is caused by the economic recession in 2007. And this large dip here is the reduction in emission caused by COVID-19 pandemic. I have added to this this bar here in red. That's the extra emission caused by wildfires in the western United States. So as you can see, the western wildfires almost cancel the reduction in emissions caused by COVID-19. Transportation industry is becoming more efficient. As you can see, the number of electric vehicles used are continuously rising, while the number of internal combustion engines have been continually dropping. Shipping industry has become much more efficient over the years. So this is data from 1855 to 2006. And these are kilograms of fuel used per 1,000 tons moved distance of 1 mile. So as these go down, that means very large increases in efficiency for the shipping. Same thing has been happening in the transportation aircraft industry. So, for example, this is a Boeing Dreamliner. These are kilograms of fuel used to move 1 passenger forward by 1 nautical mile. So low numbers are good. This is the Boeing 787. This is the Airbus A380, which was not as efficient, and unfortunately, it is being discontinued. Drop in life cycle CO2 emissions for aviation. So see a significant drop and a continuous drop in emissions. Again, these are grams of CO2 per revenue passenger kilometers. We see a dip in early to mid 2020 caused by COVID-19 in energy consumption in all sectors, followed by gradual recovery to pre-pandemic levels. COVID-19 has increased awareness of the public to the growing need for environmental policy change. It has had an effect on election results in many countries. Europe has dedicated the large amounts of euros for the recovery fund, and economic downturns historically have led to changes in technology, such as more efficient methods of transportation. This is the well-known S-curve in relationship to electric vehicles. So we are around here where the growth of electric vehicles is going to rise, and obviously it's going to flatten after a few decades. The number of electric vehicle used is dotted to light blue, so you can see that as we go down from 2015 to 2030, this blue part is getting bigger. So there will be a significant increase in use of electric vehicles. And I have data on various countries and various manufacturers, which I will go through very quickly. The states of California and Massachusetts in the United States are going to ban the sale of gasoline and diesel fuel new cars by the year 2035. Norway has made significant progress in electric vehicle area. It is the largest oil producer in Western Europe, with the market share of electric cars increased to 54% in the year 2020 from 42% 1 year before that. United Kingdom is going to ban the sale of new cars running on fossil fuels 9 years from now. Many different countries plan to many different manufacturers plan to discontinue gasoline and diesel-powered vehicles, as shown here. So Jaguar is going to do that in 2030, Lotus in 2028. General Motors says it will make only electric vehicles by 2035, and similar results for Ford, Volkswagen. And of course, as electric vehicles are used, it is anticipated that it will have a positive effect on reduction of CO2 emission. Global sales of electric cars are shown here from the year 2010 to 2020. That's this graph here. And this yellow one is China, for example, and these are Germany, US, and United Kingdom. As in summary, in the first few months of the year 2020, COVID-19 quickly swept through the world, and it was declared a pandemic on March 11th of 2020. There was a lot of slowdown in the economy, many lockdowns, stay-at-home orders, social distancing, limiting air travel, particularly to diminished air travel to near zero, and obviously there was a reduction in the use of fossil fuels and CO2 emissions. Many cities experienced periods of clean air and blue skies not seen for generations. The positive effects on the environment have been drastic, but very temporary. The wildfires in the United States alone in the year 2020 resulted in additional CO2 emissions, which was almost the same as reduction in the first half of the year 2020 caused by the pandemic. Renewable energy has advanced tremendously, but fossil fuels still supplied 84% of the global energy. Advances in aircraft efficiency and the use of electric vehicles are very encouraging. Electric grids must quickly adjust to the additional power demand for electric vehicles. It is expected that it's going to cost $1,700 to $5,800 per electric vehicle to upgrade the electric grids. That's the end of my presentation. Thank you very much for your time.
Question on the room or on Skype?
Yep, I have a question. Okay, so thank you for your presentation, Mr. Promoajahed.
You're welcome.
I was shocked that the wildfires undid the positive effect of COVID-19. Is there any way to predict the wildfires, to use the climate data to undo the negative effect of wildfires?
Well, I was personally shocked myself. The calculations are very simple. We have the number of acreage which we use as a unit of surface area, like hectares here. So we have data on how many hectares burned, and you could quickly estimate how many trees were there and calculate the mass of the wood that burned. And when wood burns, a lot of it becomes CO2. So the calculations are very simple, and we have checked it multiple times, and it is correct. And I was shocked to see that too. That for the first 6 months of the year 2020, as a result of the pandemic, we see 2.5 gigatons of decrease in CO2 emissions and 1.7 gigatons of increase caused by the wildfires. So if you add to it what happened in the Amazon and Australia, it is very alarming. It looks like preventing wildfires or reducing their size is going to be much more effective than a lot of other things we are doing. And so some wildfires are necessary and natural, and they're caused by lightning and things like that. But data shows that 90% of wildfires are caused by people just being careless. Campfires, wind, so they don't stop the fire completely and they just walk away, and you start the wildfire. Cigarette bullets, you know, they're very hot, so people go hunting. These hot bullets just fall on the grass and start the fire. So, yeah, I was surprised as much, and I think there's a lot that can be done to reduce those things, and I think that can have a very, very immense positive impact on reducing the effects of climate change, more than a lot of other things that we are doing. I hope I answered this question.
Yes, fully. It is very unfortunate that humans are one of the main causes, because it's one of the most difficult causes to prevent.
That's right. That's right. And I think education of people could have, the power lines that go down. That started a lot of California wildfires last year and resulted in major lawsuits, and the power companies had to pay billions of dollars for damages just for that. And as a result, their stock went down very quickly and all of that. So there are many things that can be done, and I hope they will be done, because most of these are caused by people.
Thank you.
Thank you very much for your presentation. I have a couple of questions. The first one is related to the first question is related to the previous presentation. Have you measured the temperature after the wildfires? I mean, as you know, when there is a volcano, it is often the temperature around the world decrease about half or 1 degree. Then have you analyzed the temperature after the wildfires in California or in other places?
Well, the temperatures that we refer to are average global temperatures. So we're talking about small changes, 0.7 degrees, 1.5 degrees, things like that. Clearly, if you are in the middle of a wildfire, the temperature rise is much, much bigger than that. So a lot of houses are burned, and the data is collected from space. So from space, using satellites, we clearly detect the fires and see the intensity of the radiation coming from them. So that was some of the data I was showing as bar charts. So that radiative power of fires measured by satellites, and those are the numbers that I was showing. But I've never seen any individual data on actual temperatures at a place where you have these fires. These are usually measured from the sky.
Okay, I say that because, as you know, there are some variation, local variation of the temperature. For instance, here in Almeria, as you know, there are a lot of greenhouses for agriculture. There are some studies done by researchers at the University of Almeria who have shown that while in Spain and the surface of Spain has increased the temperature 1 degree, about 1 degree in the last 30 or 40 years, in the area where the greenhouses are located, the temperature has decreased more than half degree because the reflection of the sun. I say that because probably with the large number of wildfires in California, especially in California, we have seen this information 3 years ago, and also in Portugal about 1 decade ago. There is interesting also to analyze the temperature, not at this moment, but some months later. Okay? It was only a question in order to observe also the impact of the temperature in the global area in order to analyze possible cycles in the future.
Yeah, well, thank you very much. I haven't seen any data like that, but that sounds very interesting.
Okay. And the last question related to the second presentation is that, in my opinion, my personal opinion, well, there is a big problem with the electric car, because perhaps not in the USA, because in the USA there are many people living in flat, not in flat, but in houses, independent houses, and they can charge the cars inside the house. But here in Spain, for instance, and I think that in many places in Europe, it is not possible, because we live more than 70 or 40% in buildings where it is not possible to charge the vehicles. Then I think that it will be a very big problem for especially poor people, or people not living in large houses. Then, for me, it's a bit, I wonder, we are speeding up this situation in Europe and also the USA, that I agree that has some advantage, but I see that in China, for instance, they are constructing so many power plants. If the weather is global, I think that we are solving a very problem with an ice port, but in China, I don't know exactly because there is not many public information in the mass media about India, but India is going to be the largest population country in 25 years. And it is to solve a very local problem with an ice economic port in some countries, because the USA has about 350,000 million people, Europe 400 million people, but we have there that I have read just now that in Reuters there are also many information in Bloomberg, etc., that say that China is constructing more power plants, 3 times the power plants that there are remaining in other countries. I think that the local strategy, we are doing a local strategy which in global will not reduce significantly the big problem we have with the environment. And I think that it is not coordinated with China, India, etc. Well, we can solve the 5% or the 10% of the problem, but at the end they will have, because we have sent the industries, and we have not the control of the emissions. The control of the emissions is where there are the industries. Then the industries are in Asia, and I don't know exactly which is. My view is that the global situation will not improve so much with the action taken in Europe, in USA and Canada, etc. If China and other countries are not involved in this situation. Then I don't know which is your opinion.
Well, that's a very good point. When it comes to charging the vehicles, I think the solution is wireless charging, which is a fairly new technology, but it is growing rapidly. So just like we are doing most everything wirelessly right now, I mean, with our phone, we could get so much done. The laptops, you don't have to hook up to anything anymore. Same thing is happening for charging of electric vehicles. So it can be done while you park. You don't even have to plug in anything. And there are roads being developed now that they charge your electric batteries while you drive. So just like 200 years ago when they had gasoline engines, it was hard to find gas stations. Maybe every major city had one fueling station, but now we see them everywhere. So I think the same is going to happen with charging stations, because the technology is moving very rapidly. But I agree that there is a problem now if you live in a big building with a lot of apartments and there's no place to plug in. Yeah, that is a problem, but technology will take care of it. It will take maybe a few decades, but we will be there.
And what do you think that will be the role of the United States in the reduction of these emissions?
I think it will be very positive because everything pointing in the direction that they are supporting. All the conventions like the Paris Agreement and all of that, so they will be back in full force.
Because you are in the second position of the list, so I ask for you.
Yeah, I think that, you know, United States is going to be a partner with Europe, and they're going to significantly contribute to the effort to reduce the CO2 emissions.
Okay.
Well, I think I've used more than my time.
Yeah.
Thank you very much for
You're welcome.
everything.
Thank you very much.
Okay, the next.
Next paper will be optimization of energy accumulation for renewable energy sources by Milan Baek.
Okay, thank you for the introduction.
Sorry for that. So another coefficient describes the behavior of the battery system. So you can see here a very brief description of SOC coefficient. So the state of charge of the battery, but it also affects the economic aspects of the battery. How you operate with the SOC, it affects the life cycle of the battery itself. So again, you have many variations and many different needs of various customers. Someone focuses on the maximum usage of the battery, someone can focus on the maximum life. It depends. And again, it could be described maybe on some coefficients. And the last coefficient should describe the regulation capabilities of used power sources. And what is the result? You can see on set of various pictures, and I will try to explain the different situations. Here is the basic diagram, and yes, you can see the pointer. And please focus on that brown curve that describes the energy that is consumed by the consumer. So it is not important if the energy comes from the grid or from the microgrid. But here you can see that we reach some threshold, and it means that the energy that would be consumed above this level must be covered by the grid. The question is it okay or not? It depends on the customer if he uses the strategy of the peak shaving or not, but it is just to describe this compatibility. Another picture looks very same, but now we can focus on another curve, and you can see here the state of the battery. You can see that the battery is almost the entire day fully charged, or almost fully charged, and after reaching some threshold, it is this line, it activates the algorithm to decide if to charge or not to charge. You can see if you compare these two curves, so this is the customer needs and this is the state of charge of the battery. So it is evident that in this part of the day, part of the energy is covered by the energy of the battery. You can see that the state of charge is decreasing. Now it is almost discharged. But you can see that even if the customer needs more energy, the battery is started to be charged. From this point, it starts to be charged. It looks rather strange because it could mean that you will need some energy from the grid. Now I must explain one specific situation from our country. We have various tariffs, so you can consume in various time on various price. So it is very, very complicated. So also it looks very strange that you need the energy, but you charge the battery, but you charge it from the grid. But this is caused because you have the own costs. So the algorithm is able to predict that in this time, as you can see, the consumption is still decreasing, but it is not able to charge the battery from the photovoltaic because this is almost the evening, and it is not reliable to charge it fully from the grid. So the algorithm starts even here, even if there is the lack of the energy. It looks sometimes very strange, and it was very confusing for us to understand what the algorithm does, because you will see on another picture, I know there are many curves, but it is necessary to see all of them because all of it describes complete behavior of the system. So it was very difficult to understand how the algorithm behaves, and also the behavior of the algorithm depends on the hardware it uses. And it is another very important thing, because we try to use the as cheap hardware as possible. So the algorithm must be fast. And depending, it is very strange, but depending on the conditions, so if I return on my first pictures, for example, on this picture, depending on this shape, it affects the speed of the algorithm. If everything is constant and you only change the prediction, it affects the speed. So it is a very complex problem to optimize the algorithm to run with sufficient speed for all the situations. So you can see here is the reference coefficient with a different value. And you can see on these pictures 0, 90, 0, 90, and all the other coefficients are the same. And you can see there are always small differences, even if the coefficients has changed. So here you can see that there is a value between the stability, between the costs, between the operation compatibilities, and between the battery 0 to 1 to 100 to 1/2. So it is almost unbalanced. And what happens if we change the balance? So it means that the customer uses, for example, the battery with a different value. Here you can see that the battery, has value only 1/2, and here is the battery charged for 1. So it means that the value or the life cycle for the battery is more important for this customer. And you can compare different shapes. It is best evident on the blue curves. In this area, you can see that in the same situation, the system behaves in different way. So it is evident that this system or our algorithm is able to cover all these needs, but the last question is the speed. And it is evident on this picture because the time window here is longer, and it is the last thing that affects the speed. As I explained, this shape affects the speed, and we must take into account that there is a certain time window that moves slowly along this time. And how long is the window and how complicated is this diagram, it also affects the speed. So maybe, and it was proven, maybe it is better to normalize this diagram, so not to use it too curly, but to make it more smooth, so to use some input data, but to prolong the time shift, the time window. And in fact, you can compare the last shape of the state of the battery. Here you can see various charging strategy of this algorithm, even if this algorithm was tuned for 75 steps. It means 75 moments in the length of 6 minutes. And in this case, the time window was 145 elements with 6 minutes. So it looks very complicated, but in result, it was possible to modify the algorithm that was designed previously for the diesel engines to operate and to control various types of renewable energy sources as photovoltaics and as the wind turbines. It wasn't tested on the hydro plants because the regulation compatibilities are very close to the diesel generators, and we focus on the microgrids that are typical in our country, and it is not usual to use the hydropower plants. So typical customer uses either photovoltaic or the wind turbine, or maybe both systems together, and maybe coupled with some battery storage system. So at the end, this system was modified. The speed was increased, so it is possible to use the cheap RDL modules. So the hardware is very cheap. It could be purchased in, let's say, below 100 euros. And this system can control the microgrid with installed power in, let's say, 10, 20, or 100 kilowatts. And it could contain various types of the consumers and various types of the producers. So that's all from my presentation. I thank you for your attention, and now I'm ready for some questions.
Questions on the room or in Skype? No. I have only one question. I just want to know if, in your opinion, the different tariffs for consumers is useful?
Yes, it is a very complex question. I must return to this chart because it depends. In our country, there is another specific situation. I'm not sure how does it work here, but you can have something that is called, let's say, a reserved load. So, from the technical point of view, you can connect, let's say, 100 kilowatts. It depends on your power lines, on the cables, on the protections. So, let's say you can have 100 kilowatts.
Yeah, it's different.
Yeah, but in fact, you can have only so-called reserve power, and it could be, in our case, let's say 20 kilowatts. So, theoretically, you can use 100, but from legislative point of view or from commercial point of view, you use only 20 kilowatts. And if you use more, it is technically possible, but you pay the fees. So you can, but you are charged. And some consumers, it is typical example of this chart. For example, in this picture, you can see that the maximum consumption is 140 kilowatts. Okay, so it means that your reserved power should be 140 or better 150, somewhere here. It means that you will never reach this moment, so you will be never charged. But you pay for this reserve power some amount of money, let's say 100 euros. But if you decrease the reserve power for, let's say, 100 kilowatts, it means this. You will pay only, let's say, 50 euros, so it is much cheaper for you, but in these moments, you will be charged. And now is the question, what is for you more economically profitable, and even if you can cover these peaks with your own production, so with your microgrid. So it could be very interesting if you connect your microgrid and cover only these peaks, and the rest you cover from the public grid. Is the question. So it depends on the customer's needs. I know it's very complex. There are many various things, and it all affects the economic profits, the technical needs. So it's a very complex question, but it could be controlled by this algorithm. So even if you want to just to control these peaks, or if you can, or if you want to cover entire needs, it depends on you.
Thank you. Any more questions?
Yeah. I have a question regarding the grids and the technique you're using. Okay, so for the environment or for the efficiency, does the government or the provider of the electric system let two grids communicate between each other and share the energy? And your strategy could help both, not to get the profit, but to make both systems not consume out of the grid, maybe.
Yeah. In our country, it is very complicated because, for example, I will use this long chart. So you have installed power of photovoltaic, let's say 140 kilowatts. So you can cover all your needs. But in most of time, you have some overproduction. And the question, it is your question, what to do with this overproduction? You can sell it. You can simply not to sell, but just to let it flow to the grid. But in this case, you will be charged. So even in this time or in the rest of the day, if you are producing the energy and you don't need it, you will be charged. You supply the energy into the grid, but you will be charged. So probably it is for you more profitable if you use this energy for your own consumption, or if you can sell it to another concrete consumer. But it is very easy to say, but very hard to manage. It takes plenty of paperwork, so it is not a usual situation. Or you can use battery system. And now the question is different. You have battery system, so you must pay some purchase costs, and of course some running costs. So what is better for you? To lose the energy, to profit zero in this time, to supply it to the grid and to be charged, or to pay for the battery system and probably to profit from this energy in these moments. So, in fact, I'm not able to answer this question because there are many variations and many different solutions depending on the customer's needs. So, probably you can use the battery system, so you will be more efficient. It is evident. But will you be really efficient from the economical point of view? That's the question. It is a very strange question. It is sometimes very absurdous, but it is the real situation, unfortunately, for now. The situation will be probably changed and it will be more easy to sell the energy for the other customers, but for now it is very complicated. It is theoretically possible, but very complicated. So the cooperation between your power source or your grid and the public grid is possible, but...
Okay, thank you. You have answered my question, and the second question I was going to ask you about the cooperation between, like, using the public grid as a transport medium only.
Yeah.
Okay, so for now you are being charged, and maybe in the future they are working towards a different system.
But you are charged for several reasons. At first, you are charged for the number of the reserved power. So this is this number. It depends on your consumption, on your needs, on your power, and this is what you really technically need. And if you overcome it, you will be charged. So if you want to sell some energy, and the most simple case, you have some power station, maybe PV power station, with 120 kilowatts. So your reserved power will be 120, this amount. So through entire day, you can sell almost all your energy to the public grid. It is okay. It is your contract. But if you overcome that limit, the reserved power, so if you overcome the 120, it could be some very sunny day, like here in Almeria. It sometimes happens also in our country. So you will have some overproduction. And in this case, you will get some money for this amount, but you will be charged for this amount. So again, the question is, will you really profit? So the question from technical point of view, is it really good for you to sell all this energy or to lose it somewhere else? If I return, for example, to some household consumers, it is maybe profitable if you install maybe some air conditioning. So you want to install photovoltaic system, but it is not profitable for you. But if you will install photovoltaic plus the air conditioning, it will be profitable. It is very strange, but unfortunately it works in this way. So sometimes the customers are very discouraged from this strategy and from this system because they should work, but they work from the economical point of view very strange. It is unfortunately so. So that's the reason why we are trying to solve all these situations, even they are very different. Because there is no best strategy. It depends on your power needs, it depends on your reserve power, so the money, it depends on your technical options, it depends on your ambient options, so on the, let's say, on the weather forecast, on weather conditions, and it depends on your technical solution. How you have the system connected. Is it coupled with some battery storage system or not? What kind of battery storage system? How old? How you behave with the batteries? So there are many questions, and it is very complicated to recommend to some customer the best strategy, because there are many ways, and not every customer is or knows best the way, or No, mostly the customer doesn't know what he really wants. He say, I want the economical profit, but what does it mean? Yeah, is it really just the purchase cost, or is it the purchase cost plus running cost, or can you focus only on the running cost? Because the battery system, of course, means that you could be independent. And how you can describe this criterion? I am independent, so how much does it cost? How can we compare this? So it is very, very difficult to explain to customers. These systems are in fact new, so the people have almost no experiences with that. So maybe they have some expectations, and it is very difficult to fulfill these expectations.
Thank you very much.
So, thank you, Milan. And then the next presentation will be IoT monitoring system for applications with renewable energy generation and electric drives, and it will be online.
Technical University of Athens. We are very happy to present our paper in the 19th International Conference on Renewable Energies and Power Quality. Our project is Internet of Things monitoring system for applications with renewable energy generation and electric drives. Our team is comprised by professors and PhD students from National Technical University of Athens, from University of Thrace, and the School of Telemic Programming of the University of Madrid. In what follows, we will present you the scope of our project, the equipment that we have used, the two experimental systems, and conclusions. The scope is the development of our laboratory Internet of Things based system for electrical machines and analysis of two applications: control of electric drive motion and control of wind energy generation system. Our aims are first to update the existing laboratory, second, provide students with the applied up-to-date knowledge on control systems with Internet of Things. The equipment that we have used is mainly electric motors, electric machines that are used for power generation, networks, Wi-Fi connection, online internet platform, Azure from Microsoft, and of course the power grid. For data, there are many sensors that have been used, and for the control system and the server, we have used a Raspberry Pi. And for user interface, we can use either a laptop or a mobile device or a tablet, anything that has access to the internet. Our first experiment is a system to control a three-phase induction motor over the internet. And this motor gives the mechanical energy to a DC generator, which in its turn gives energy to an electric load. So we have the energy flow system, which is
220, 30 voltage and 60 hertz frequency. And on the other hand, we have a Raspberry Pi, which is programmed to serve as a server. And this Raspberry Pi also controls a USB adapter that in its turn drives the inverter, which inverter drives the induction motor. On the other edge, we have an optical encoder, which measures the speed, the frequency of the axis of the motors, and gives this data to an Arduino, which in its turn provides the data back to the Raspberry Pi. Also, we have sensors to measure power and voltage and current, which are opto-isolated for protection, which provide this data to an Arduino, which again provides the data back to the Raspberry Pi. The Raspberry Pi concludes this information flow and concludes the feedback by sending data to our web application, which is uploaded to the Azure cloud platform. And of course, we have a user interface we can access it through any laptop or any device that has internet access. Particularly, we can see that some details for the usage of the experiment of this system, and some explanations regarding the way that all are collected and collaborate together. Please feel free to pause the video at any time so that you can, if you are interested in, you can read further more information regarding our experiment. The second experiment is a system that controls a three-phase induction motor, which drives in turn a double output induction generator. So the difference here in the energy flow is that we get energy from the network in our laboratory. We provide it in the induction motor. The induction motor drives a double output induction generator, which in its turn, with the appropriate control, provides back the energy to the network. So in this experiment, we have a different approach, which is the Raspberry Pi through the USB adapter, the RS485, drives the inverter that drives the motor, induction motor, with a variation of frequency simulating the variation of wind power. So it's the Raspberry Pi provides random variations of frequency, which drive the induction motor as it would be if it would follow the variations of the wind. The second inverter that drives double output induction generator has the role of correcting these variations of the power produced by the induction motor, so in order to provide high quality current back to the network. Again, we have sensors that provide data to the Arduinos, and the Arduinos send the data back to the server, to the Raspberry Pi. Again, the Raspberry Pi has a double role of providing data back to our web application on the Azure, and of course, we can access our server through any computer or laptop or smartphone that's connected through the internet. And this concludes the information control. Again, we have some details regarding the usage and the collaboration between systems. Please feel free to stop the video at any time and read if you need any further information. Finally, our conclusion is that after presenting the design and implementation of the two experimental configuration of IoT, we can see how IoT helps us to remotely connect the power generation and the drive units with the usage of microprocessor and controls. Of course, we can see that the future is of controlling and monitoring such systems is going to be more cost effective and more easy to be applied by more people due to the fact that the coding is much more easier than the previous versions like PLC and stuff like this. So the 10 added value involves data acquisition from sensor, data analysis, device and connectivity, and decisions for controlling and monitoring with the usage of microcomputers, hardware, software, and an integrated remote control system. In the laboratory, we upgraded with IoT connected device and sensor software and intelligence algorithm, open a new research perspectives, especially when we managed to connect the motors that were produced in 1970. So, having developed an IoT infrastructure, the laboratory offers an environment for teaching, research, in design, and also implementation and testing of smart industrial applications with induction motors and smart wind power systems with double induction generators. Thank you very much. This was Stasas Tamelos from National Technical University of Athens. We wish all the best for all of you.
Any question on the room or on the internet? No. So the next paper, it's effects on pulse frequency on performance of electrochemical cooling water treatment for cooling tower of water cooled.
Everyone, I'm Lê Minh Nhật. I came from Vietnam. Now I presentation with of my study with title Effect of Pulse Frequency on Performance of Electrochemical Cooling Water Treatment for Cooling Tower of Water Cooled Chiller. The content of the presentation. The first introduction, second material and experiment setup, net result and discussion, and finally conclusion. The objective of this study, we focus on the effect of pulse frequency on the electrochemical technology on the efficiency of total hardness removal of cooling water to attain the required cooling water quality for cooling of the water chiller, and besides the effect of operational parameters such as the power duty cycle, current density, and energy consumption on total hardness removal efficiency are considered. The introduction, as you know, cooling tower are an integral component of many water chiller, and which are used to recheck the wet heat of the condenser. The quality of cooling water of the cooling tower of water chiller is effect on the consumption of the water molecule and is the effect to the coefficient of performance. When the formation of scales in the water cooling system, the deposit of calcium carbonates on the wet surface in the condenser water system at insulation and reduce the heat transfer efficiency of the condenser of water molecule, and therefore we need water cooling treatment for condenser. And now have many methods to treat for the cooling water. Just we focus on the electrochemical cooling water treatment. How about the electrolysis process, the anode reaction and cathode reaction, and also hardness of content bicarbonate ion, and in hard water containing bicarbonate ion, the reaction process at the equation from the 1 to equation 5, and relationship between the phospholytic cycle and post-cycle T and phospho frequency extract at the equation C to equation A. Experiment set up in this study it's in figure 4 and figure 5. The schematic diagram of the whole electrochemical cooling water treatment for the cooling tower of the water molecule shown in the figure 4 and figure 5. This system was designed and installed on the campus of the Ho Chi Minh City University of Technology and Education of Vietnam. It's mainly consists of the power DC power supply mode, a cooling tower, a condenser connect with the cooling tower, and electrochemical reaction tank and electrodes, and 2 pump for condenser loop and electrochemical reaction tank loop, measurement device and control board. The power DC power supply can be adjusted to the potency according to the experiment. And design and discussion. And figure 6 show the change in the efficacy of the total hardness removal during the reaction areas of the pulse efficiency, which increase in the pulse frequency range from the 0.1 kHz to the 30 kHz. Efficiency of the total hardness removal increasing gradually at the beginning and reach at the high value of the 86% at the pulse frequency of the 1 kHz. And figure 7 shows the effect of the pulse frequency on the total hardness as seen in the figure 7. During the first 60 minutes, when the concentration of hardness ion in the cooling water is high, the electrolysis reaction occurs rapidly, leading to a rapid decrease in total hardness, and then total hardness decreasing gradually due to the concentration of the hardness ion that relate to the decline of frequency on the TDS index was shown in the figure A. There is no difference in the reduction of TDS index when the pulse frequency from then the 0.1 kHz to the 30 kHz. During the first 60 minutes, the TDS rapid decreasing and then gradient decreasing with the electrolysis term. At the pulse frequency of 1 kHz, the TDS index dropped. The practice of at the 1 kHz from the 0.3 milligram per liter to the 126 milligram per liter. The low TDS index indicated that the metal ion sat at Ca2 plus and Mn2 plus in the cooling water are low. The effect of the whole duty cycle on the efficiency of the total net removal and energy consumption as shown in the 7.9. By increasing a pulse duty cycle from the 0.2 to 0.7 lead to increasing satellite the efficiency of total net removal and reach the highest point of the about 88% at the pulse duty cycle of the 0.7. The effect of current density on the efficiency of total net removal and energy consumption shown as in the figure 10. As indicated in the figure 10, one of current density range from the 10 AF plus square to the 80 AF2 per square. The efficiency of total net removal increasing from the 74% to the 95%, and the energy consumption increasing from the 35 watt hour to the 23 watt hour. When the current density grows more than max than 80 per square, the efficiency of total net will tend to be steady, and while energy consumption continually increasing. Conclusion: in this study, the effect of the operating parameters such as pulse frequency, current density, and pulse duty cycle, and energy consumption on the performance of high net removal of electrochemical cooling water treatment for cooling tower of water cooling chiller was evaluated. For the purpose of the quality of cooling water after the tip work obtain the required water quality of the quality standard of Vietnam. These are show that the efficiency of total net removal is high as the value of the pulse frequency is 1 kHz. The value of the pulse duty cycle is 0.7, and the value of current density is 88 per square. Thanks for your attention.
No question. So we are closing. Thank you for your attention, and we are closing the oral session B5. Este es vuestro, ¿verdad? Vaya lío, yo no sé cómo vais a hacer.
No lo sé, si es tuyo o nuestro.
¿Vale?
Ese es mío. Ese es mío.
Voy al baño. La otra es la principal, ¿no? Sí.
Esta la otra, esta la principal.
Vale, voy a ir al baño antes.
Sí, yo pensando.